Good. Yeah. So the plan of this lecture is something called as online resource allocation. So till now, we've been looking at a bunch of stochastic problems and more specifically general techniques for learning large classes of stochastic problems, monotone stochastic problems in particular. This lecture is about somewhat, I would say, more specialized, but a very important problem, something called as online resource allocation. So the high level objective is going to be again the same. It's a very important problem, online resource allocation. There are simple solutions if you know the distribution. And now the question is, what can I do when you don't know the distribution? You have like some samples or something like that information. So you want to do data-driven stochastic optimization, but for this class of problems called as online resource allocation. Good. So what's roughly the setup of the online resource allocation? You have some requests coming one by one. The notation I have is n requests for m limited resources. Good. So in this particular example, like your resources are like some burger, grass, carrot, and you have a bunch of requests. Again, depending on your background, so sometimes these are called requests, sometimes these are called buyers in the context of auctions. In some other context, it's called users. These resources are called items in many settings. Yeah, one can use whatever terminology. At a high level, the point is these requests are coming one by one. Each request can be satisfied in many, many ways. Your goal is to satisfy the request, but depending on how you satisfy it, it's going to consume some amount of resources. And it's going to generate some reward. So this slide is a bit informal. Next slide, I'll make everything super formal. So, but the high level goal of resource allocation always is just like you have a bunch of requests coming, and you need to satisfy them to usually maximize the value. So you want to make everything like total value that you're generating from the allocations while satisfying the resource constraints. So if I had infinite resources, then problem is easy. Basically, I'll satisfy each request in the way that basically gives me the highest value. Maybe for each request, I will assign them every possible resource. But usually resources are bounded. And now the question is, how can I kind of, what's the right trade-off between assigning resources versus generating value? Good. And this is even offline. So offline resource allocation, sometimes people say like the field of economics is nothing but all about just resource allocation, how to allocate scarce resources. So I'm saying like it's a very broad problem, but I'm saying somewhat, yeah, you can still think of this as a specific problem rather than say a broad area. And online setup is nothing but like these requests are not given to you upfront. These requests come one by one. So maybe first the bunny shows up. Bunny says, maybe I'm interested in a burger or a carrot. So simplest example would be something like a matching. So you have these items, you have these requests. Bunny comes up, bunny says, I'm interested in like a burger or a carrot. You need to assign one of them. Then a penguin comes and so on. You have to assign these resources. And as I was saying, this is a very fundamental problem. So simple things like how to sell a house, hiring a job candidate, shipping industry, hotels, flights, ride sharing, scheduling problems, adverts, like all of them can be thought of as in the end, there's some resource that's being allocated to a bunch of users and you want to maximize some kind of a value. The resources are limited, like your flight tickets is about resource allocation, finding a job candidate, there's like one or two slots that you have. You want to get the best candidate. So all of them are just about resource allocation. So what I want to say is like, it's a very, very important fundamental problem. All good? So this was the informal slide. Now let me make everything the same thing, formal. Okay, so the setup is the following. So n requests come one by one, sequential requests. Whenever the ith request comes, it reveals you three things. One is the value function, one is the consumption function, and the third is the decision set. So maybe for simplicity, you for a moment think of matching example. So in the case of matching, it would say something like, if when the ith request comes, it says that the decision set would be like, these are some offline vertices, you can match it to. So there are these different potential vertices, you can match it to. These are different resources. You need to assign only one of the resources. Depending on which resource you assign, you are going to get some value, which is maybe think of the weight of the edge. And the consumption will be like 1 unit of that resource. Whichever offline vertex you assign it to this online vertex, that's basically 1 unit of resources consumed. But in general, you can define this like much more broadly. Your decision set could be much more abstract. There are like, I mean, I'll talk about these examples like linear programming or something like that. You can think of actually actions which allow you to even simultaneously assign multiple resources. So you don't have to restrict yourself to just like a matching that a request can only be satisfied by assigning a single resource. It could even be much more complicated. And it could even be of infinite support and so on. Like, yeah, but maybe for concreteness, it would be best just to think about matching. So basically, yeah, some request comes, like the bunny comes, it says there are two possible options. The action set that you have is basically whether you assign them the first or like the burger or the carrot, or maybe you assign them nothing. That's also an option. If you assign them nothing, then it generates value 0. If you assign them the burger, it generates maybe $10. If you assign them a carrot, it generates $100. You need to decide whether you want to allocate, maximize value, subject to resource constraints. Good. So maybe formally, you want to maximize over theta is the decision set for the ith request. So maximize over all I, the total value that you generate, vi theta, subject to that the total consumption that you have. This is a m-dimensional vector. M is the number of resources. So AI is I'm thinking of this as a vector, m-dimensional vector. It should be the first resource budget is B1, second resource budget is B2. Every resource like has a budget BI. Like in the extreme case, maybe each of the budget is just one. So you have exactly like one copy of every resource, every item. You need to assign them to maximize the value. Any questions? And usually today we'll be interested in the so-called competitive ratio. Again, most of you probably already know this, which is the total value that your algorithm generates compared to the hindsight optimum. Yeah, to the hindsight optimum. So we'll be interested in this benchmark. And the reason is more like because this is often like a stronger benchmark. And although for many learning problems, you cannot actually achieve good competitive ratios, the regime in which we'll be studying this online resource allocation, it turns out we can even get like very good guarantees in terms of competitive ratio. So by the way, the title said online resource allocation with large budgets. It would basically mean for each item, I'll assume I have like large number of copies. I don't have like just a single copy. So there's like a lot of work on online resource allocation with like small budgets as well. Yeah, but the results we'll talk about today, they'll be like in some sense, yeah, I think much more relevant for this workshop. Good. So again, maybe to give some mathematical example, like online bipartite matching is something I already talked about. You can talk about problems such as online routing. So what is a routing problem? Maybe each time step you have a graph, some SI-TI pair appears. You need to send some flow between them. So basically resources are the edges of the graph. So if you assign them a path, that's in some sense, some kind of a resources that you've consumed. And depending on what path you assign, you could, there are many, many actions. Actions basically represent what path you assign to meet this SI-TI request. And you have some constraints on the edge capacities. Online packing LPs. Here, the setup is usually, yeah, like you want to maximize some like V transpose X subject to AX less than B. So ith request is basically the ith column of the constraint matrix arrives. You have to, so constraint, like the ith column is AI. You need to immediately set xi. Let's say xi is between 0 and 1. So how much of this column you want to take so that the budgets are satisfied? Like capital B, like bold is basically the B1, B2, B3, this vector. And depending on what fraction of this ith request you take, you get some value VI. So there's like similarly, there are more general combinatorial option settings where you maybe have like the value functions could be like submodular functions, XOS functions, subadditive functions. So yeah, all I want to say is like, yeah, there's lots and lots of work there, yeah, in this line of direction. Perfect. So if the basic model is clear, yeah, please interrupt me if something is not clear because, yeah. Yes.
Is the budget have the same dimension as the resources? Like is every budget specifically linked to a resource or could it be?
Yeah, budgets are linked to the resource. Yeah, for the first resource, how much budget I have, second resource, how much budget. Yeah, exactly. So budget exactly represents how many instances, copies of a resource I have. And for simplicity, often it helps to maybe think of budget is the same for everybody. Okay, and usually techniques extend. Let's say like I have some B copies of everybody. B is the same thing. Okay, good. And so, okay, like the high level question is basically, can we come up with some online resource allocation algorithms that have this competitive ratio very close to one? So can I somehow, although I'm getting these requests one by one, I want to satisfy these requests to generate the maximum value. Ideally, I want to generate value which is very close to as if I had known all these requests upfront. And that's what like the ratio is, the alg value, total alg value versus the total hindsight optimum value. And we want this ratio to be very close to one. Question?
For everything start with the B.
Good. So I'll be making a bit more assumptions. Yes. So as the way I have told you right now, yeah, B vector is known to you. What will happen is actually these requests that ith requests that are coming, they'll actually be from some distribution. So the distributions would be known to you upfront, but not the realizations. Good. So for instance, this is like the so-called profit inequality problem that again Paul was talking about during this week. So this again, like it captures profit inequality problem as well, because in some sense, you know, requests are coming from some distribution, you don't know the realization. Okay, good. So we'll be actually a bit more ambitious in this talk. So we'll not be interested in just in designing any algorithm that gives you like a good competitive ratio, a good maximum value. We'll actually be interested in something called as posted pricing algorithms. So maybe to give you an example. So again, let's say there are a bunch of items and you actually go to a grocery shop. So again, in grocery setting and like basically in economic settings, often the objective is you have all these resources. Resources basically means like maybe milk, bananas, whatever, different kinds of things. They are priced at different rates so that basically people who value it more, they get it. You don't want a setup where you don't want like, first of all, you don't want to price the item so high that nobody takes them. Also, you don't want to price them so low that everybody just takes them and wastes them. So nobody gets like a good value out of it. Like the society, you want it to be max, like the welfare to be maximized, the total yearly value. So such algorithms are called posted pricing algorithms, where before a request comes, I'm going to set some price for all of the resources. So rather than running arbitrary algorithms, I want to actually run some posted pricing algorithms, which basically means before the arrival of any request, I'm going to set prices for all these items without looking at the request. And then the decision that will be chosen or the action that will be taken for the ith request will be the so-called utility maximizing. In some sense, you say that person, like whosoever is the next request comes, you can buy any resource that you want, you just have to pay for it. So what would you buy? Basically, you will buy like if lambda is the price, AI is, remember, recall the resource consumption function. So you'll pay additively. So if you want resource like 1, 5, and 7, one copy of each, you'll pay the price of lambda 1 plus lambda 5 plus lambda 7. So, and what as a user, as a, like the ith request, the way they will choose is basically maximize the value minus the resource consumption. So maximize over all possible ways you can satisfy this request. The value that it generates minus this. Because I'm thinking of this ith player coming and yeah, choosing for them. So it's basically, or maybe like if this is getting too abstract, like this is exactly how the way you would do at a grocery shop. So you go to a grocery shop, there are different items you are interested in. You'll buy a subset of these items. That whichever subset you buy, that gives you some happiness, some value, but you have to pay for it. So I'm going to maximize my happiness minus the payment that I do. And that's what is a posted pricing algorithm. Good. So why am I saying this? Is because like I'll be, for this online resource allocation problems, often we are interested in not just designing an arbitrary algorithm that maximizes my total value. I'm much more interested, especially for many of these auction related applications, I'm interested in designing a posted pricing algorithm. So it's an algorithm that literally places a price on items every time a new request comes. And then the decision I make is literally just take the utility, like this value minus price. This difference is called sometimes utility. So that's why I'm calling like, or let me call it the greedy action. So it will basically take the greedy action. Good. And why the algorithms are useful is because they are very easy and fast to implement, much useful also implement, like very useful in practice. They have lots of implications to like auction design and so on, something called as truthfulness. And one can also show they're like very robust and they'll be also very compatible with learning applications. And the high level question is, okay, I'm restricting myself even further. Then the question becomes like in some sense, how do I set and update these prices? I mean, that's the underlying objective. Does it make sense? Yeah. So like the main objective of this talk will be, I want to design good algorithms for online resource allocation that maximize my total value. First is I want to maximize my value. Secondly, I would also ask that, okay, can I actually achieve a high value maximizing algorithm that also simultaneously uses just a posted pricing that just makes allocations based on prices? And then the third part would be, okay, what if I don't even know the distributions? What if I only give you some samples? All good? Okay, perfect. So the high level question is, yeah, how to get a 1 minus epsilon approximation to the hindsight optimum? Is this a posted pricing algorithm? Good. And so that's the objective. And like to achieve this objective, we'll need kind of two assumptions. So one we'll need is that these arrivals cannot be arbitrary. They cannot be fully adversarial. You need to know something about the underlying distribution. So we'll assume some kind of a stochastic arrival, that these requests come from some underlying distributions that may or may not be known to you, but the modeling assumption is there exists some distributions that is generating these requests, some independent distributions again. Yeah. On the request, and each request is actually a triplet: VI, the consumption function, and the action set. So yeah, so basically, yeah. So I'll assume that for different i's, they are independent. But for the same I, this VI, AI, and theta, they can be correlated. So they could be arbitrarily correlated, but different i's, they need to be independent. Good. And then the reason you need, so the reason you need some kind of a stochastic arrival is like the typical example. Like if these numbers, you had no idea about their valuation, that they're fully adversarial, then you can always construct these bad examples of the kind, like the first request maybe generates you $1. If you meet it, the second request generates like $1 billion, second generates like a billion square, billion cube. It keeps increasing up till some point, and then you get all zeros. And sometimes your algorithm doesn't know when to stop. So like in the sense, like you can make, and let's say, and the same challenge appears, let's say even if you have a single resource, and even if you're in a high budget regime, like where you have like B copies of a resource, you kind of get like B attempts to stop. You can argue that, yeah, your success probability of your algorithm will only be like B over N, competitive ratio, because you don't know when to stop. In some sense, there are like so many requests, and yeah, so there are simple reasons to argue why, you need some kind of a stochastic assumption. The other assumption will also be like we'll need like budgets to be large. This is what I meant. And large budget would roughly mean that each resource has roughly 1 over epsilon squared copies at least. So it gives you like a good trade-off and one can show again like these factors are tight, that in some sense you cannot hope to improve better than 1 over epsilon squared. So to get say like a 90% approximation, you need epsilon is 0.1, so you need like roughly 1 over 0.1 squared budget. Does this make sense? Good. Okay. So if everything is good, then here's like the outline for this part of the talk. Like I just defined what is online resource allocation. Why is this like a very fundamental problem? Appears in many, many fields. Depending on your background, I mean, you care about auctions, you care about solving LPs or something else. It appears in many, many settings. And like what we are interested in, designing good algorithms for online resource allocation. Ideally, we want these algorithms to also be not an arbitrary algorithm, but a posted pricing algorithm. The plan for the next part of the talk is, okay, let's say for the moment I know the distributions. Then I claim there is a simple algorithm. There's just a simple solve LP I can write, linear program, and I can just do randomized rounding, and that already gives me the right trade-off. In the sense, to get a 1 minus epsilon approximation, it turns out you just need budgets to be at least 1 over epsilon squared. So this is the setting where you fully know the distributions. That's what I'll show you next. And then the reason we'll not be satisfied with this is because of two reasons. One is it needs to know the distributions exactly. What if you don't know the distributions? The other annoyance would be that it's not a pricing based algorithm. It's some LP rounding. So it's difficult to implement in practice, and like other benefits of pricing algorithms are lost. So the next part would be unknown but IID distributions. So these requests come from some IID arrivals. And in the next talk, I'll talk about also like when the distributions are not identical. Okay, let's make it a bit more formal. So now the model is the following. You have n requests, ith request. So this is like a more formal model. Ith request comes from some known distribution di. The assumption is the distributions are first of all known and they are independent. So the first request comes like maybe if you're comfortable, maybe thinking of the matching setting. In the matching world, it would basically mean the first request comes. And so you have a distribution on what edges, potential edges would be incident to this vertex and what are the weights of these edges. So there's a distribution, there's a joint distribution on the edges and the weights. And then your algorithm has to immediately make a decision where to match it. So you have known independent distributions. And the objective is the same. Immediately, whenever you receive a request, you have to decide how to satisfy it. You'll get some value and you consume some resource. Goal is to maximize value subject to some budget constraints. One assumption, because I'm making this large budget assumption, I'm going to assume that no request consumes more than 1 unit of a resource. So in some sense, nobody is ever interested in getting like 10 copies of an item. So 10 copies of the same item. So the reason this will be needed is like because I was making an assumption that I have at least 1 over epsilon squared copies of every item. This assumption only makes sense if everybody is interested in at most 1 item. Because if otherwise, like it's kind of scale invariant. Like if, yeah. Good. So that's the assumption. And so now the plan would be like I'll basically give you a very simple linear program for this problem. And then we'll just do LP rounding, simple randomized rounding, apply Chernoff bound, and we'll be done. Good. And how would we write an LP? I mean, so let me write this LP for the simplified case where let's say each ith request has only support size 2. Like so ith request is either Vi with probability Pi or 0 otherwise. Okay, so ith request has only 2 options. So in the bipartite matching setting, imagine a distribution which is of the kind that with some probability the ith vertex shows up. Otherwise, the ith vertex decides to skip today. So you're selling a bunch of items and like you have n potential customers. With some probability, the ith customer shows up. With some probability, it does not show up. The only reason I'm making this assumption is because the LP is cleaner to write. Otherwise, you can, I mean, in general, you can have like 1 extra variable and you can sum up over these k variables. Yeah, so but now what the LP looks like is the most natural one. So you have variables xi theta, which basically means when the ith request comes, what's the chance I satisfy this request by doing action theta. So I'm maximizing summation over I and theta, xi theta, vi theta, subject to my budget constraints, that the total consumption of the resources on average should be at most my budget. For some technical reasons, as we soon see, I'll have to slightly scale it down by 1 minus epsilon. This is to make my Chernoff bounds. Okay, I mean, but let's say I don't have this factor for a moment. So then this is the LP, where this is just saying the resource consumption. And I will say like for any request I summed up over all actions, this is at most Pi, because Pi is the probability that the ith request shows up. If the ith request doesn't even show up, then I'm guaranteed that I should not even satisfy it. I'll always perform. So yeah, I guess I did not maybe say it explicitly today. Yeah, I'm always assuming there's a null action, which means you can always skip a request. Like if you run out of budget, if you run out of resources, then it's not that your algorithm has failed. It just means that for all the future requests, you'll perform the null action, which basically means you will just reject the request. So you'll not get any value, you'll not consume any more resource. So I'm always assuming that in your decision set, you always have the option of playing the null action or the empty set. Good. So now the claim is that, okay, without the 1 minus epsilon, this LP is clearly an upper bound on even the offline optimum, because all these constraints will be satisfied even by the hindsight optimum solution, where I take xi theta to be precisely that theta is optimal for ith request. Yeah.
Specify that for ith request, we select the optimal that which maximizes the average.
So I'm saying we don't specify it, but this is an LP relaxation. So if I know the distribution, if I solve it, it has the option of even deciding for the ith request, whatever is the optimal action, that's a feasible solution. So that's a feasible solution. So whatever this LP returns is only potentially of higher value. So up to this 1 minus epsilon factor, but if you scale down the budget because everything is linear, that can hurt your optimal value up at most by like a 1 minus epsilon factor. So the claim is that this LP value is a valid upper bound on the offline optimum, hindsight optimum, up to this 1 minus epsilon factor. Good. So yeah, so just the simple, this is what I'm saying. Like if you solve this LP, you'll get some solution xi theta star. This objective value is an upper bound on the benchmark up to this 1 minus epsilon factor. And the plan will be, so now basically, if I can give you an online algorithm, which gets, again, like roughly this LP value, then it will say that, okay, online resource allocation, at least algorithmically for known distributions, can be solved. You can get a 1 minus epsilon, like 1 minus order epsilon approximation for this problem. Because this LP is an upper bound, so if I can get you some like 1 minus epsilon fraction of this LP benchmark, then I'm done. Yeah, does this make sense? Good. And like as I was saying, like how will I achieve it? I'll just do LP rounding, standard LP rounding. So what will I LP do is for the ith request, whenever the ith request comes, whatever is its value, then I'm going to choose the corresponding fractional solution. I guess, okay, I've changed, like, yeah. So, I mean, here the LP was written where I was just assuming whether the ith request comes or not comes. In general, if you have more complicated, like the ith request can potentially take different, like ith vertex could be of very different kinds. You have a support, which is a distribution, which is more complicated. Then you can just like sum up additionally over k everywhere. But yeah, I mean, it's not super important. The point is basically I'm saying like whenever the ith request comes, roughly I'll go into play an action based on the LP solution. And the claim is this will be a very good algorithm. It will give me a 1 minus epsilon approximation. And the algorithm is basically I take the LP solution. LP will tell me like, okay, this is the resource I want to assign it to you. There are two situations. Either that resource still has budget. If the resource has budget, you'll assign it. If the resource does not have budget, then I'm just going to stop the algorithm. I'm not even going to take any future request. And the reason it works is it's going to be like a 1. So the claim is that it's 1 minus epsilon approximation as long as every budget is roughly 1 over epsilon squared up to this log factor. And that's just like Chernoff bounds because recall like the way I wrote my LP relaxation, I had the upper bound was b times 1 minus epsilon. So in expectation for any resource, I'm going to consume at most b times 1 minus epsilon copies of that resource. So what's the chance that this randomized process that you're running, it ends up consuming more than b? Okay, so the expectation is b times 1 minus epsilon. And these are sum of independent random variables. Like for the first request, it consumes this resource with some probability. For the second request, it consumes with some probability. So what's the chance that if your expectation is b times 1 minus epsilon, what's the chance that you exceed b? This is the standard application of like a Chernoff bound. So that's precisely what happens. So we just need to argue that basically no resource is exhausted till the end. So we can just apply the Chernoff bound. The expectation is b times 1 minus epsilon. Whereas what's the chance that this sum of random variables where the expectation is b times 1 minus epsilon, what's the chance that it crosses b? The simple Chernoff bound says that as long as b is like 1 over epsilon squared, this is not likely to happen. The reason you have to lose a log m is precisely because I want to take a union bound over all the m resources. So if as long as my budgets are at least this roughly like log over epsilon squared, then I can argue with high probability all the resources will not be exhausted till the end. So does this make sense? So I'm not maybe going over the Chernoff bounds exercise in very detail, but I'm saying nothing fancy is happening. It's just saying that, okay, or maybe you think of it like if my budgets are like at least 1 over epsilon squared, what's the chance that you deviate too much? By up to 1 minus epsilon factor, it's extremely unlikely. All good? Okay, so this is a decent algorithm. So the main two drawbacks of this algorithm are the following. One is that it needs to know the distribution because it needs to solve this LP. Only if I have this LP solution, extra stars, only then I can physically perform this randomized rounding. That's the first drawback. And the other drawback is also it's not like a pricing based algorithm. Ideally, I wanted some kind of a posted pricing algorithm. And that's where we'll head next. So maybe let me skip this slide. Yeah, so the main takeaway from this part is that if the distributions are known, then you can write the very simple natural LP, perform an LP rounding. It gives you a 1 minus epsilon approximation as long as the budgets are roughly 1 over epsilon squared. In this talk, I'll not care too much about log factors. So let's not worry too much about the exact dependency on the log M or whatever. It's not a pricing algorithm and it cannot be solved. It requires you to basically know the LP and the distribution to solve the LP. If I had known the distribution, then you can solve the LP even efficiently. There's something called demand oracle. You can, let me skip that part. But the main question is, what if the distributions are unknown or how to get a pricing based algorithm? Perfect. So the next part of the talk, I'm going to focus on again the same problem under one additional assumption. So one assumption will be like the distributions for all the n requests will be identical. It's not ith request is coming from some ith distribution. These are IID requests from some fixed distribution, fixed but unknown distribution. So the crucial thing is it's an unknown IID distribution. And then I want to design a good algorithm. So what's funny about this problem is that somehow like for all the learning or data-driven aspects like that we've been talking on during the week, it's usually that I'm giving you some samples upfront. In this case, in some sense, I don't even need to give you samples upfront because these are NIID requests. I can learn as I go. Like I can use the first few requests to learn whatever I want to learn and then hope to use that information and exploit it in the future. Because these are literally IID requests from the same underlying distribution. So I don't even need to know any offline information upfront. Questions? Good. Yeah. So the question is, unknown IID with large budget basically means 1 over epsilon squared budget. How would I get a 1 minus epsilon approximation? Okay. Good. So again, I'm repeating the same thing. So n requests IID from some unknown distribution. Each request, just to remind, is like the value function, the consumption function, and this is in set theta I. Your goal is the same, maximize total value generated subject to the budget constraints. It's a m dimensional, like it's a high dimensional problem because you have m resources. There's also the related random order model where these requests are not coming from some distribution. There's like some worst case n distribution that somebody fixed, but then their arrival order is chosen uniformly at random. Turns out almost all the things that I'm going to talk about, they apply there as well. But let's keep it simple. Let's just talk about the IID model. The proofs just get a little more complicated when you talk about the random order model. Or like a fancier word is so-called exchangeable sequences. But so let's not talk about. And this is like a problem that has been greatly studied. Some of the initial results go back to like Bobby Kleinberg, which is 20 years ago. He studied this problem for single resource. So the question was, if I have a single resource and I have some B copies of it, what's the best possible approximation ratio I can get? So he showed that you can like the right trade-off is roughly like you can get a 1 minus 1 over square root B. So if B is like 1 over epsilon squared, then you can get a 1 minus epsilon approximation ratio for the so-called, he studied it in the random order model, the secretary model. He called it the multiple choice secretary problem, but basically it's the same thing for single resource. In high dimensional setting, it was first studied in Devanur and Hayes. They did not study the full general online resource allocation problem, but a special case of this for some adverge and matching settings. Then people studied it like Agarwal, Wang, and Ye, like 2014, 2010. I think this is the journal paper. The conference version appeared around 2010 or so. So there were like many papers, and then they were trying to achieve better and better bounds. So although the problem was already studied in Devanur, Hayes and like these papers, early papers, it's only like around like 2015, 16, people achieved the optimal trade-offs and the optimal bounds for this unknown IID. But in some sense, like for 10 years in between, people were trying different variants to get the right problem. Exactly this problem, unknown IID arrivals for this multiple resources. So what's the the objective is to get 1 over epsilon squared. Roughly 1 over epsilon squared budget suffices to get a 1 minus epsilon approximation without knowing anything about the distributions upfront. Any questions? Like a brief history. Good. So let's maybe try to do some simple exercise first. Let's try to do even like solve this problem for a single resource. That's getting closer and closer to what Bobby Kleinberg was studying in 2005. So suppose I have a single resource. I have B copies of it. In other words, think of it like you have n numbers coming one by one. You can select at most B of them. And your goal is to maximize the sum of these numbers. Because it's a single resource, you don't even have to think about higher actions. It's literally just whether I accept the number or not, I don't accept the number. My goal is to maximize the sum of these B numbers. What algorithm would I run? And these numbers are drawn from some unknown IID distribution. I don't know the distribution. Is the problem clear? So let's try to design an algorithm for this special case, and then we'll generalize it to higher dimensions and so on. Okay, good. So the problem is clear. So the main idea like on which the algorithm is based is if suppose somehow somebody had told you out of these n numbers, let's say these numbers were fixed, if somehow magically you knew the bth largest number. So let's say B is like 100, you were supposed to select 100 items. You want to maximize the sum. So if somehow you had known the 100th largest item, largest number, then the problem is trivial. I'm just going to set this as a threshold right from the beginning. Numbers come one by one. Any number that's above this threshold, I'll take it. Otherwise, I'll reject it. And also this kind of tells you like connections to this pricing algorithms, because in some sense you're setting a price. Anybody who's willing to pay me this 100th largest value, whatever that is, if I know this number, then I'm done. Because I can set this as a price. Anybody walks into my market, they can buy it, one of the 100 copies of the item that I have, and I want to maximize the total value generated. Good, and that's precisely the idea. And the only thing that's missing is how would I learn this 100th largest number? I mean, I don't really know the 100th largest number. And also there's like some stochasticity, but like in some sense, because I'm in an IID world, when I say 100 largest number, I really mean like in some sense, the expected number, I want to find a threshold such that the expected number of numbers that will be above this threshold will be roughly 100. Because remember, everything is stochastic IID. So 100th largest number is also like a random variable. So I want to learn some kind of a threshold such that the expected number of numbers that will be above this threshold will be roughly 100, or my budget, or budget up to like a 1 plus minus epsilon factor, like all of these things. And that's precisely what we'll do. Like, so we want to set a threshold such that the expected number of elements above is roughly B times 1 minus epsilon. Okay, so instead of maybe 100th largest number, I'm going to set like the 95th largest number as my threshold, just so that there's like a slight slack of 5 numbers. And this doesn't hurt me too much up to this 1 minus epsilon factor. And here's a very simple idea that you could do is for the first small fraction, some epsilon fraction of the items, like the numbers that are coming, these are IID numbers, just reject all of them. Don't take any of them. The intuition is, okay, this should not hurt me too much because I have like n numbers coming. I've only discarded epsilon fraction of my input. So maybe epsilon opt value is gone. It's fine. I can afford it. Use this small first epsilon fraction now to estimate this 100th largest number, or like the bth largest number, or B times 1 minus epsilon largest number. Learn some decent approximation of that, and then set that as the threshold for the rest of the 1 minus epsilon fraction of the time. And that's precisely this first algorithm. The algorithm is discard the first epsilon and requests, set a threshold, which is roughly not the bth largest on the request, like out of B optimum elements, roughly epsilon B of the optimum elements will land in this first epsilon fraction. So I'm going to set a threshold to be roughly the epsilon Bth largest element in the first epsilon n elements. That's up to this 1 minus epsilon factor. That's my threshold. For the remaining 1 minus epsilon n arrivals, I'll just select anything which is above this threshold. That's the algorithm. Does this make sense? And the claim is this will get you some decent guarantee. It will not get you the optimum guarantee, but it will give you a decent guarantee. Because the intuition is literally this, because you're in the large budget setting, B is like 1 over epsilon squared or something. So this first step that you have, it will not learn you exactly the bth largest element. It will learn you some decent approximation. And if you actually play with the parameters a little bit, turns out this will give you like you need B to be at least 1 over epsilon cube. So you don't get 1 over epsilon squared, but you get something like 1 over epsilon cube. If you just want to, like, because I have to kind of apply extra concentration at this first epsilon B, like the first small epsilon fraction. So if you do like play with the numbers, apply Chernow bounds carefully, naively this will give you something like 1 over epsilon cube, which is already pretty good. Like it's not 1 over epsilon squared, but at least it's decent. Any questions about this thing? Like, is the algorithm and roughly the idea of the analysis clear? I mean, this is like a nice exercise to attempt offline, just to get comfortable with the setting. And turns out you can actually, like a slight modification of this algorithm will allow you to improve this 1 over epsilon cube to 1 over epsilon squared. So like currently the algorithm is, it's also called as like the explore exploit kind of, again, this thing. For the first epsilon fraction, I'm just going to explore. I'm not going to take any decision. I'm not going to accept anybody. I'm just going to try to learn for the first epsilon fraction. And for the remaining 1 minus epsilon fraction, I'm just going to exploit. No more learning anymore. I've chosen my threshold. I'm just going to take numbers which are above this threshold. So this is in some sense some kind of a two-phase algorithm where you first just learn and then you just exploit. Turns out this gives you 1 over epsilon cube. And naive, like a natural way to improve this, and that's what works, it gives you 1 over epsilon squared, is don't stop learning. I mean, as you're going, continue learning. Why have you like just given up? Like right in the beginning, you'll have a very bad estimate. But as time progresses, you have more and more samples. So you should improve your estimate further. Like you have a better estimate of the bth largest overall. So use that. And that's precisely the trick that allows you to improve this B to the like 1 over epsilon cube to 1 over epsilon squared. So the trick is literally like do the standard powers of 2 trick, like use the first 100 slots to learn some decent estimate. For the next 100 slots, now I have like 200 samples. I'll use this 200 samples to learn something for the next 200 rounds. So now I have like 400 samples and 400 to 800 and like repeat this like logarithmic times. And so I'm like learning and exploiting. So it's not the same price that I'm playing forever. Like these are like powers of 2. And you work out the math. Basically, it will give you like this 1 over epsilon cube easily improves to 1 over epsilon squared. Question? Yeah. Yeah. So I mean, okay, naively, it will lose you like a log 1 over epsilon factor. So it's a union bound over, but the number of rounds is only not too much, or maybe like it might lose you like a log n. I'm being sloppy here. And like I don't care about the log factors in today's talk. Turns out you can do a more careful analysis. The same algorithm, you don't even have to lose the log. Yeah, but that's, I mean, yeah, that will require care. Like you have to be very careful about with the analysis. If I don't care about log factors, then it is easy to prove. Yeah.
Well, doubling trick is for the analysis, right? There would be no reason not to recalculate every time to learn from all the samples you have so far.
Oh, you mean... Sure, I think like one can argue that you could recalculate every time step rather than just like powers of 2. Just that I'm sure that analysis will also work out. I guess at least provably it doesn't give you anything better. Yeah, so I mean, yeah, so you could do extra computation. And maybe in some instances it performs a bit better, but in the worst case, I think it doesn't help. Yeah. So yeah, you could recompute if you want. Usually we want to, in some sense, actually avoid extra computation because we want faster algorithms. Good. So in some sense, like, okay, this presents you pretty much the full story for single resource. If I have a single resource, this algorithm is again nice because it's, first of all, getting me the right trade-off, like budget needs to be only 1 over epsilon squared. And it is also pricing based because I'm literally like learning my prices as I go. Yeah, it's a pricing based algorithm. So it has all the advantages as well. It doesn't need to know the distribution. Everything is happening on the fly. You can apply the same intuition to higher dimensions as well. So maybe, okay, I'll finish in like 2 minutes. So turns out this was first observed by this paper of Devanur Hayes and Agrawal Wangye. Turns out you can apply similar intuition even in higher dimensions. In higher dimension, okay, it doesn't make sense. By higher dimension, I mean like you have now not a single resource, you have m resources. So now what does it even mean to learn a price? Like earlier I had something like the bth largest is a very good price. If I have n numbers, if I can get you the bth largest, then in some sense, I want like anything above that, that's the optimum. In high dimensions, things are now trickier. But you can show actually by LP duality and so on that there is some kind of a m-dimensional price, which is like kind of the dual of the linear program that works well. Using the same argument, then you kind of want to repeat the analysis and argue that, okay, if there is, I want to learn some m-dimensional price vector now, rather than a single price, such that again, like the expected number of items that like some expected number of resource consumption due to like resource consumption for these prices will roughly be b times 1 minus epsilon. The challenge, I mean, the algorithm I want to run is again of the similar kind. First epsilon fraction of the input I'll discard, use those epsilon fraction to learn some m-dimensional price rather than a single price, and then use that price for the rest of the setup, the rest of the time horizon, 1 minus epsilon fraction. Naively, the number of prices is infinite, but you can use some standard, like I think there's something that Rohit also talked about, the epsilon net argument. That although you are in a m-dimensional space, naively there are infinitely many prices, but I can discretize things to like multiples of epsilon. So the number of prices will be roughly, potential prices will be of the order of like 1 over epsilon to the m. And then you apply like a union bound and Chernoff bound and so on each of these price vectors. So that will lose you like a log of 1 over epsilon to the m. So you get something like m log 1 over epsilon. And that's precisely the reason. So this result will give you something like m over epsilon cube. So in 1 dimensions, I was getting 1 over epsilon cube. Budget needed to be 1 over epsilon cube. In m dimensions, you get something like m over epsilon cube naively. But then again, like this doubling trick that we were talking about, you can apply that to get something like m over epsilon squared. Okay, so long story short, whatever intuition that we discussed in 1 dimensions can also be applied in higher dimensions. But to get basically something similar, like with single shot learning, you get something like m over epsilon cube. But if you do the doubling trick, you get m over epsilon squared. So this is a decent bound. One thing that's not good about this bound is like when we saw LP rounding, the dependency on m was only logarithmic. Now the dependency on m is linear. And for many modern online resource allocation applications, you work with settings where like many resources are there. Like suppose you're assigning ad slots to different kind of requests are coming, you have like thousands of resources. So a lot of the work that happened after this was on, okay, I want to, this naive bound will give me something like m over epsilon squared. Can I get something which is like log m over epsilon squared? And that's what we'll discuss after the break. That basically, yeah, so maybe I'll not get into that slide, but let's take a maybe 10-minute break. So after the break, we'll see like how one could hope to improve. Again, the same setup, same model, IID arrivals, how to this m can be improved to roughly like a log m over epsilon squared. And yeah, and then we'll also briefly talk about non-identical distribution. So this proof will have like nice connections to things like multiplicative weights. A quick question, how many of you have heard of or like seen multiplicative weights before? Okay, so 50%. Okay, I'll briefly go over it. Okay, cool. Yeah, let's take a break.